Today we have three outstanding scholars who will present the exciting report on ORB-SLAM, thin film linear neobate device, and visual vibration analysis. I hope everyone will actively participate, ask valuable questions, and engage in depth exchange with the speaker. First, let's welcome Professor José M Montiel, who will present on ORB-SLAM, a versatile and accurate monocular SLAM system. Please join me in welcoming him.
Okay, can you hear me? Good afternoon. Well, I am going to start the presentation with the ORB-SLAM system. This paper was published nearly 10 years ago. So I am going to make initially a broad view of the system, and then I am going to switch to more recent results that has been derived from this system. So first thing is what a map is. The idea is that, well, this is a map, and all of us has this idea that it's something that expresses geometrical information or geographical information, spatial information coding. But this is not the only map that we can have. We can have different maps. For example, this treasure map from a pirate, in which we are interested in a treasure, but the localization of this treasure is not explicitly in the map, but it is in relationship with other elements. So you can represent the localization of something which is hidden or which cannot be seen. The tube map is interesting because the important thing here is our stations, and we really don't care where the stations are. What is relevant is if there is a connection between two of them. We are interested in connections more than in localization. The typical navigation map. And also I am interested in this kind of maps in which what really you have is an evolution in time to understand how there are variations geographically localized. Well, but having a map is not very useful compared if you don't have where you are within the map. Now we are in China, we are out of this map, so I go to my normal localization, which is here. So to use a map, you need to know where you are in that map. Typical localization methods for telling you where you are GPS. So you have a satellite constellation to tell you where you are. The question is that we don't always have this infrastructure, and maybe we also don't have this map. For example, if we are a mobile robot and I would like to operate, for example, under this table, no one is going to come before me to build this map. I have to build it by myself. And also, I don't have here GPS accurate to tell me where I am. So this is our goal. Being able to do a map by our own means, and we also being able to localize within this map without needing any external infrastructure. The only information that we are going to use for making the map and for localizing within the map is going to be a camera. So this is the ORB-SLAM system that is able to do this. So here, the understanding of this video is that this is a camera which is in front of a car. The system selects some few points, and this is top view. In this top view, we have represented, I'm going to stop this, yeah. So the system selects some random points in the image, and then for this, all of these green points are these black points that you have here, because this is top view. And the actual localization of the car is this small triangle here. And the question is that as we process the video real time, we are able to make the map and to know where we are within this map. An important thing here is that when the camera explores new areas, this map is being extended. And when we come back to a place where we have been before, we are able to reuse the map. This is what is going to happen here. Now, we are able to reuse this part of the map. Now, we explore. So, we go to some new areas. And here, we are reusing this area because we already have the map. And when we go out of this area, we build again our own map, expanding the actual one. This is what's happening here, and this is the trajectory that the car has followed. Well, how accurate this can be? Well, here you have a lateral view of the let me see if I am able to put there. Yeah. Well, when we built the map, we didn't have any prior information, but the car is moving in a flat area. So this is the floor, and these are the trees, the windows, everything that was on top of the floor. And in this case, the size of this scene is something like this is something like a quarter of a kilometer. So this is the kind of maps that we are able to build. Well, the question is that for doing this map, we are using monocular cameras, and as you may know, a monocular camera do not have depth information. So here, we don't know if the hand is from a giant, if this is a toy tower, or if it is an actual person hand and the tower is just far away. Because of that, we see small one. Well, this is the bad part, but the good part is that with a camera, we don't detect depth, bad for us, but the good part is that we can detect objects at any depth. There is nothing so far away that a camera cannot detect. This is, I could say, in this conference I have to be careful with plenty of theoretical physics around. This is the end of the universe, and we can see this with a camera. Basically, a telescope is like a camera. Well, so my focus is going to be geometrical information. So when I select a pixel, click in an image, from a geometrical point of view, what I am able to know is, with respect to the camera, is the bearing of that pixel, this angle and this angle. This is for every single pixel. Additionally, on top of this, I get the color of the light coming from that bearing. And magically or nicely, one image is 1 million of bearing angles. If instead of one image I have a video, it's 20 frames per second, 1 million images, geometrical information, very accurate. So we would like to make the most of this accurate geometrical information. So how do we recover depth? This is very basic in computer vision. Is ideally, if we have two images, then if this camera is located here, this camera is located here, we compute the intersection. In an ideal world, this works. In real world, what happens if we try to do this? These two rays never meet. This is quite good news. Why? The fact that these rays do not meet is telling me that either my estimation of the camera poses or the matches that I am using are wrong. So I have a criteria to really check if the geometrical model I have is right or not. Well, if we go to the camera's point of view, this is the scene, this is my camera, this is the image I have. What I would like to compute is where this 3 point is and also where this camera is. Making a projection, I can make up a hypothesis. I assume that the point is here, I assume that the camera is here, and I can check. If the point is here and the camera is here, this point should be projected here, but actually the projection was here, so this is my error, and this error is telling me how bad is this point with respect to this camera. So with this simple equation, I am able to compute the geometry of the scene. If we go to the images, it's the same case. We have two cameras, we have the 3D point, we have where it projects, and we have two errors. So what is our problem? Our problem is just try to make these two errors as small as possible. And then what we get end up having is an optimization in which we optimize the reprojection error. So we find the best camera poses, the best 3D poses to explain the images that we have. Well, this is quite old, and we can trace back to 2006. The first use of this method proving that it can work with images, general images. Maybe you know this experiment, and this experiment, they go to internet and ask for pictures of Fontana di Trevi in Italy. They get all these pictures, they compute the matches between the images, and from these matches, they are able to make this model, which basically is computing where were all the photographers that took the pictures, and also a 3D model of the scene which is being observed. Well, in SLAM, we are going to use the very same equations, but there is a difference. I will refer to this method like SFM, and in opposition, I am going to speak how do we deal with the video that we are processing in SLAM. So, in structure from motion, they use collection of images which are an order. However, we have a video, and we make the most of the video information. So we know that we have one frame, and then the other, and then the other, and then the other, quite close to each other. The whole images here are processed as a whole, and we process one after the other. So we have the video, we have an estimation about where the camera is, the new frame comes, and we correct the camera pose. The new frame comes, and we correct the camera pose in a sequential manner. We do this in real time, so we are able to compute where we are after processing each video frame. The software reference for this processing is Colmap, also from this time, 2016, and the software reference for SLAM is ORB-SLAM, which is the awarded system. This is the team that has been developing the software, the first original paper, and some other works which are connected with this software that is very popular nowadays. Well, the whole point in this SLAM thing is matching. We have two images, and we have to be able to compute matches. When the two images are very close in time, this is a video, and then you have to match one frame with the next, which is the case, is very simple. But still, we have to do it very fast. The problem comes when the images are quite apart. So this corresponds to colonoscopy. This is the same place, but there is a significant change in the point of view and also in the lighting. So the matching between these frames is more difficult. Well, so part of the system is selecting what is the feature. In the time when we were doing this, the key feature was shift, but the problem of this feature is rotation invariant, scale invariant, is accurate, is good for widely separated views, but it's expensive. Then is ORB, which more or less has the same properties. The invariance is not that good. The accuracy can be more accurate because it's point-based. The capability to relocalize is poor, but it is very efficient. Can you vote the volume a bit down because there is a bit of coupling? Okay. Well, so the question here is that when I come back to Zaragoza, I have such a big error accumulated that the system thinks that this Zaragoza and these are different because they are located differently and because they have different size. So to correct this, what we do is we use visual localization to identify that this image and this image correspond to the same place. So this camera, instead of being where it is, it should be here. Then we propagate this correction to the cameras, but we still have the map wrong. Propagate the correction to the map, but we still have duplicated features. And then finally, we correct the duplicated features, and we have the final map with the correction. Well, here are some of the results that we obtained. This is a flying drone, and just with the camera, we are able to process and in real time compute where is the drone flying and what is the room where this drone is flying. We are computing the shape. As you can see, that the camera pose is computed in 3D, and the map is expanding as the drone flies. Well, since then, you can compare the picture. Me and Professor Tardos, which is the common person, now we are older. This is 21. We have another version of the system, and in the main feature of this new version is that it's able to handle multiple maps. The original work only have one map, and when you get lost, then you cannot create a new map and then mix. This is what we are able to do with ORB-SLAM 3. And we can also deal with the stereo cameras, not only monocular, with fisheye cameras, and we can also consider inertial information. Well, here you can see the system in operation. So this is a room in which the system starts, and now the system goes back to a very big hall in the technical university dimension. And you can see that when you go to a map where already has been built, the system is able to reuse. Now go to the next floor, go in the second floor, come back in the same corridor, and come back to the original room, and it's able to go back again. In this case, we are combining with visual inertial information. So we go back again to the big hall, jump, and now enter in a big slide, and then you can see that the system is able to know that we have gone to the ground floor and coming back to the original room because it's visual inertia. And this part of the slide corresponds to the fact that I'm going to show it here. Okay. You see? So this is proof how big the map can be and how we can handle just using visual inertial information areas as big as a great hall in the technical university image. Well, this is the first part of the talk. Now I am going to move to a recent research that we are doing, is that this SLAM system, okay, works well when you are in, let's say, robotic scenes, but now we are intending to be a bit more ambitious, and we would like to, instead of process these outdoors or indoors environments, we would like to do maps in medical imaging. So we are going to use the same methods for processing real human, in this case, are colonoscopies. So we have this challenge of going from this kind of environments to these other environments, which are significantly more challenging. I can show you this video. So compared to the images that we were handling, You have like water cleaning. You have change in the lighting because doctors like to use different lighting. You have a very strong camera motion. And the question is, how can we survive to this extreme environment and we still are able to do the maps? This corresponds to a real procedure. So you see that we have to face really a challenging situation. So what we have is the scene is no longer static, there is deformation. Here we have texture for the features. Here the texture is really poor. Here we have like constant lighting, and here the light changes a lot because they are using different lamps, but more importantly because the light is joined to the camera, and when the camera moves, the light moves. Well, then there is a European project which is called Endomapper, in which research is being done, and this is our ambition. Our ambition is when you are having a procedure, the doctor sees the procedure, but also sees a map which is specific to the patient. And our idea is, as I have mentioned, yes, we are doing the map, but yes, we would like to know where we are within the map that we have built. And we understand that this can be very useful for navigation, for helping the doctors initially, but in the long run, we think that this is the basic information for an autonomous robot moving inside the human body. Well, this is the consortium where the research is being done. And these are the typical challenges we have to face. Scene deformation, we have water in the lens, we have dark scenes, we have tools operating, we have water washing, and we have to deal with all these challenges. And as previously, the question really is matching. Are we able to really detect separated pieces of information? And well, the first step that we have done, going with this traditional approach, is, as I mentioned initially, ORB was good, more than good. ORB was cheap and not bad, but SIFT was good and expensive. So what we have done now, we have go to GPU implementation of SIFT and just run to see what happens. And well, the result is not bad. This video that we are going to see corresponds to the second, which is the end of the human colon. And we are going to reproduce something like this, but with these images. So here, so you can see it's similar. And here the important thing is that, as you see, the system continuously loses track and starts a new map. Lose track and starts a new map. But at some point, it's able to merge all of them of these maps. Here, I'm going to stop it. Here it is. Now we have the scene, and here the trajectory, which is in colors, means that this full scene is the merging of 4 different trajectories, because as you have seen in the video, there are interruptions continuous, and then you have a submap, for example, the yellow, another submap, which is the green, another submap, which is the blue, and finally it's able to merge all of them in a unique map. We can see something similar here. Maybe this is a bit nasty, this part. Not that much. This is the upper limit of blood I am going to show. So they are really operating here. The system nicely survives despite the deformation. So we know exactly where the camera is with respect to the scene. Now there is this cleaning of the lenses, this watering. Now the system loses track, but is able to mix all the trajectories, more cleaning, because this is something they do continuously, and the system is able to survive. Another challenging situation, which is very frequent, happens here. They are exploring this area, and then they go in, I don't know why, and then they go out, they are in the same place, and the system is able to mix. So now they come back to the same place, and they complete the map with all the views that they have from this cavity. And they survive despite the change in light and despite the deformation that may be in that scene. Well, the problem that we have now from a scientific point of view, a methodological, is that we are computing now a piece of information that cannot be computed with other sensors. There is no any medical sensor that is providing you a model of the body and the camera pose at frame rate. So to do some tests, we use a phantom column, which is made of plastic. And then in this case, we can compute how accurate is the trajectory because we have a ground truth trajectory in this data set. So you have an idea, the accuracy we get is in the order of 3.5 millimeters after scale compensation because these models are after scale. Well, regarding deformation. Here so far we have assumed that the scene is rigid, but medical scene is never rigid. So here we are going one step further, and between the points in the map, we assume that there is a link, which is a viscoelastic link. So this prior avoid big deformations. Additionally, we have like a limit, and if there is some of this string viscous friction pair that extends over a limit, it is broken. So we are able to deal with situations like this. So this start, and like as before, we are able to compute the camera motion, but now the scene is no longer rigid, but we compute trajectories because there is deformation. And the scene topology change, and the system breaks in two parts. This work here, which is the liver, and we also have some experiments. This is simulated colon in order to have ground truth comparison, and this is real colonoscopy in which we can see the variation of the connections because there is some deformation in the scene. Well, so what is happening when we are mapping the column, as you have seen, is that we continuously get lost. So we have like small maps, and we have a map here. Here we are lost, and then we have another map. So we know that once you are here, you are able to go there because once you have gone. And this is similar to the tube map. We have like localization, and we know that somehow we can go from one to the other. Well, so now the map that we do of the column, instead of being this shape like with nice rich geometry, is what we call a topological map, in which we have, this is a localization, this is another one, there is a connection, another one, there is a connection. So the representation that we have of the column is like a set of localizations. And then how do we use this map? Okay, we take another picture. For example, in the experiment I am going to show, this map is built today, and the same person has a medical procedure 2 weeks afterwards. This is one of the frames. And then the question is, when you see this frame, where you are in the map that you have. So what we are using is a probabilistic method that is telling very likely you are here, and with very low probability you are here. Well, how are we doing this? Well, this is a clear case of visual plate recognition. We take the image, we encode in a global descriptor, and then for the other localizations, for the other images, we compute the same descriptor. If the descriptor is quite similar, we say very likely we are there. If the descriptor is very different. We say with low probability we are there. Well, so the map building process is we start to see the video, and at some point we start to identify localization. This is another localization, and so on, another one, and then we will be covering the whole colon. So after processing the video, we have almost 100 localizations along the colon, which summarize the colon of this patient. So what happens 2 weeks afterwards? The same patient, and this is real, these videos corresponds to the same person. So when we start to see the colonoscopy, what we do is okay, this, not here. Well, for example, when we get this frame, we ask the system, where do you think we are localized? And all the places tell very likely not here. So in this point, we don't know where we are. However, okay, here. Now, as you see, there are nodes which are very unlikely, but here there is like a region in which the probability is increasing and peaks here. So this is our probabilistic map that tells you you are here. So basically what we are doing, we are comparing with respect to all of them, we are computing probabilities, and then according to a Bayesian model, we are considering the connection between the nodes, and then when we find a peak, we say we are here, and of course we have a threshold saying if we are sure enough or not. So what is the use for the doctors? You do the first procedure, you identify here a region that you like to explore again, and the second time, when maybe a different doctor comes to make the exploration, the system says go farther, farther, forward, too much, backward, arrive. You really don't need like centimeters, but just in the colon is easy, forward, backward. Well, another information that we are using for the maps, this is a very basic computer graphics with the people in the room. I asked for spec myself. And well, assuming that the surface is homogeneous, albedo is the intrinsic color of the surface, but maybe you detect different colors because of the effect of the light. A very simplistic light equation says that the intensity, the radiance that you get in a pixel depends on how intense is the light source, how far is the light source with respect to the surface that you are observing, and the angle between the ray and the normal of the surface. The important thing for me here is that when the light is fixed and the camera is moving, then the amount of light that you get from a seen point is independent of the camera position. Because of that, when I take a picture, I don't have explicit information about what is the depth of the objects. However, in the case of the endoscope, the light source is linked to the camera. Inside body in endoscopy, everything is dark. The only light source is the camera. And then what happens is, yes, in this case, if the camera gets closer to the surface, everything is lighter. And if the camera sees a point which is farther, it is darker. So in endoscopy, something that happens is that darker means farther, basically. So we have been using this information to feed a network. So we have a network that we call light depth, in which you feed an image. There is an encoder with 2 heads, and then you output the albedo corresponding to every pixel and a depth map. From this depth map, we compute the normals, so we have albedo, depth, and normals. It means that we can reassemble the image by rendering, and we compare the rendered image with the original one. So we have a self-supervision signal that is telling us if the reconstruction is correct or not. And after training this network, we are able to, from one monocular frame, we are able to compute depth using explicitly the light information. Well, compare with supervised depth in a phantom column, which is where we can have information, we get similar errors than the supervised. Compared to other unsupervised methods which use multi-view geometry, which use more than one image, the accuracy that we get is significantly higher. So this is something, a result we are very happy, because I think it's particularly useful in this endoscopic environment. So these are some examples of the things that we are able to do. And the clinical use, this depth is up to scale, but in any case, we think that can produce information for the doctors, because doctors now, they should measure the polyp size, and basically what the doctor says is, looking at it, says 5 millimeters. That's it. We don't know what this 5 millimeters corresponds, if the big diameter or the small. And we think that with these 3-dimensional maps, we can measure something like volume, areas, so kind of a more objective measurement. So here are different examples of the different 3D maps that we are able to compute from the single image. Another use case, which we think is particularly relevant, is the use case for robotics. So now, with a simple endoscope, we can produce a free space map. Of course, this endoscope can be substituted by a robot that very likely operating inside the body has a light and a camera. So these methods are able to produce easily free space information that is crucial for autonomous robot to navigate. Bien. The last part of the talk is, with the previous part, one frame, depth map. Now, what if we can use the full video to produce a dense map? Or how to better use the full video to produce a dense map? So here, the priors that we are going to feed is, on one hand, we are going to say that colon has to be a watertight surface. So if we coat the surface with an SDF, we are enforcing this prior naturally. And the other prior that we have is darker means fatter. That is something that always happens in this kind of scenes. So what we do, we take the news, which is neural rendering. You have X, Y, Z, and the two angles, and the system produces RGB and a transparency. But now, instead of representing explicitly the points in 3D, we use a SDF to code the surface. This is the original work of Neus, but we have modified in order to include in the rendering part, we explicitly include the camera pose, because this produced farther means darker. It's the only change, and the effect is quite significant. If you use the original system, you get this result. Why? Well, it is clear. These images follow 1/d² rule. Normal neural rendering do not assume that. Because of that, if you feed images that not follow the standard rendering model is not going to work. So we get significantly better results. So we think that for applying these neural rendering methods inside the human body, you have to use this illumination decline because it's the actual rendering model that should be used. Secondly, there is a very interesting medical use case for this method. Here is the ground truth. So the camera has this motion, and this is the actual column shape that we have because we have a phantom column made of silicon. In the real case, if we know the surface and we know the camera poses, we can compute what areas of the surface has been seen by the doctor. Because when you are having a colonoscopy, it's important that the doctor sees the most of the surface of the colon, because basically it's inspecting everything to find a polyp. So in this case, all these areas have not been observed. This is the model that we are able to do. So basically what is happening here is that all these areas of the model has been hallucinated because we haven't seen them. This is good because we have a model, we have the camera poses, so we can estimate what area of the colon has been seen during the exploration. So here we have an estimation about what areas of the colon that here are seen. Not very nice. You see here, this is more red. These are the areas that the doctor didn't show during exploration. More interestingly is, okay, with this you can produce a fraction of the colon being observed, but also we can provide the point of view that the doctor is going to understand best, which is from the point of view of the endoscope. Well, you have to explore the area which is behind that fold, as going to be seen now, which is the part that you miss during your initial exploration. And then the doctor can redirect the scope to the areas that needs to be observed. So, the take-home message of this talk, yes, ORB-SLAM awarded FSA award, is a popular and effective visual SLAM system. The second is SLAM in endoscopy is possible, and our understanding is now an endoscope is just a camera that is filming. At most they record the result. But using SLAM, this endoscope can be transformed in a smart device that is able to localize you inside the body, is able to do a map of the patient, and is able to produce you information for autonomous navigation inside the colon or inside the scopy. We are able to do metric maps, localized. We are able to compute from one single frame 3D models, and we are able to do dense 3D models of the colon. This is the people and the funding bodies for this research, and this is the end of my talk.
The depth from the depth from the fall off, is that for calculated on a single image? The depth from the light fall?
Yeah.
Okay. Do you try merging that with the SLAM process? So like if you have a depth estimate for each frame, then do you try sort of using that to improve the map in SLAM? Or?
Well, this was the first step. Yes, of course. The next step, clear. Now we are a humble group. So what we have done is go piece by piece. So we are able to do these maps. Yes, if you combine this and this, you will be able to do a dense map, clearly.
Awesome.
And it's going to help a lot in the process, because now when we are building the map, we don't use any depth information. So this will be very useful.
Cool. This is super cool stuff. This is very impressive. I guess one other question I had was, so you were talking about like your choice of features. You were saying, you were talking about different qualities of the features. Do you find that like in some situations, does it make sense just to use feature locations and something like ransack? Or do you always rely on feature descriptors for matching?
Well, we have different parts. For initialization, we need to use ransack because initially we don't have the motion. And then when we are going to merge two different maps, we use ransack. The idea is, as we are doing sequential, when we have a map something like one frame before, we don't need to do ransack because we know we have a very accurate estimate of the initial camera pose of the map, and then matching is just finding in very narrow regions. But when you don't have this information, which is loop closing, map merging, or when the camera has loose track, then we rely in ransack.
Okay, and so when you're not using ransack, you are using the feature descriptors, though?
And a very accurate prediction about where the features are. Because when we are sequentially, what happens is this is frame k-1, and then we have point matches, and then we have a 3D map and the camera pose. Next frame comes, and we assume that the camera is, let's say, in the same place, but the actual camera is very close. Mm-hmm. So we get a frame, and we say the feature should be here, here, and here. We make a narrow window and search for the match only here. And it happens most of the frames. And we don't need ransack here. The only case in when we need ransack is when the camera is lost, and then we see a frame. Yes, you have to find the matches and do a ransack. But most of the frames are not processed using ransack at all.
Super impressive.
Mm-hmm.
Any other question?
Yeah, thank you. Thanks for the great talk. If I understood correctly, ORB-SLAM is already in work in real time. Is that
yeah,
correct?
It works in real time.
And also my question is, can you give us a little bit, brief picture about the computational cost of the ORB-SLAM, and also if there was some sort of like a trick, if you had to apply the SLAM to the smart device, what was the trick to make it in a real time in the mobile device? So,
well, yeah, I can do. Yeah. Yes, I need something like half a minute to find a table, and then I think I can answer this question. Here it is. Okay. Well, for example, here, let's go to monocular. So here, for this image size, this is the frame rate. So here, for the place recognition, well, the system, the way it works, you have a video, and then you select some frames which are separated, which are called keyframes. These keyframes are the frames used to build the map. Roughly is 1 out of 10 or something like that, but depends if you are observing new areas or not. And then for this ordinary frames, you have to detect the features and to match using this method. And then you have to optimize the camera pose. This can be done at frame rate significantly, so it takes something like 20 milliseconds. We do this continuously. Then you decided that the camera is in a new area, and then you need to add what is called a new keyframe. Well, this new keyframe, the first thing that does is, have I seen this before? Because maybe I am in the same area, or maybe I need to mix with another map. But this is what we call keyframe rate. This processing is significantly more expensive because we have to search in a database. But in any case, the total time for detecting if I have seen this scene or not is 3 milliseconds. So in these 3 milliseconds says, this new keyframe I am going to put in the map, have I seen there before or not? Because maybe I look closer, or because maybe I have to merge two maps. The map merging takes us 200 milliseconds. And if we have to make a loop, it takes something like 500 milliseconds. But the question is that these keyframes are significantly slower than the frames, and the keyframe rate is something like half a second, 1 second. And then this map is building like, there are 5 threads running in parallel, and this is the time that it takes. I don't know if this is the explanation you need.
Yeah, and once you, or when you had to apply this method to the mobile device, so what was the major challenges or tricks to reduce the computational cost?
Well, the significant part is the capability for the tracking part to detect the features and map the features in real time, because this affects because the mapping, as it's a thread which is in background, is not that important. But all these times that are here are reported with a standard computer. And a standard computer 10 years ago. So it's something that we can do. Then we have the software, and we are granted licenses to commercial companies, and we don't know exactly, but they have managed to adapt to mobile devices.
Okay. Yeah, thank you. Thanks for the answers.
I have 2 questions. It's the first time that I heard SLAM can be used inside human body. I think it's amazing. And I wonder about the device that can be used inside human body to build the SLAM map. Is it now a cable, one side inside the human body and another side connecting to a machine?
Sorry?
Is it a cable that one side inside human body
Okay.
and another end connect to a machine?
Well, you don't really, for us, the only thing we need is the images.
Yeah.
And there are devices, for example, colonoscopy, they insert the colon, and there is a link. The same happens with the mouth. The same happens bronchoscopy. There are plenty of medical procedures nowadays that they use a camera. The camera is with a wire. But there are other procedures in which you just swallow a camera, and the camera transmits the images and moves naturally, and we will be able to process those images as well. There are other problems because normally, for example, in the case of colonoscopy, when they put the camera, they also pump air and inflate the cavity. That makes the problem simpler. But
if it's like you just said, if it's a cable in human body, it's forward, backward.
yeah.
And so is the map a one-dimensional map?
No, it's full 3D.
Full 3D.
Well, as I have said, in this part, the camera motion is full 6 degrees of freedom.
Okay.
When we go to this map, what happens is that we know how to go from here to here, but inside this region, we haven't built it so far, but you can have a small map in which you have 3D localization, full 3D.
Okay. All the physical position and angle satellite information are recorded, right?
Yeah.
Okay. So if we swallow a capsule, use the technology to swallow a capsule, can also take these pictures at.
Yeah. The SLAM technology is the only thing you need are the images.
Okay.
And from the video, you can compute what is the camera trajectory, whatever this trajectory is, and also what is the 3D that you are seeing.
I think I don't really know the advanced technology, but how is the position resolution to swallow a capsule? Can it precisely record its position, three-dimensional position?
Well, the important thing is, and this is very important, is this system do not detect where the scope is, because we really don't care.
We don't care.
We don't care. What is important for us is what the relative pose of this scope to the body surface. Maybe both moving, and in fact that happens. So we don't care where it is. The important thing is where it is with respect to the body surface. In fact, with electromagnetic technique, you can locate very well where is the camera, but it is useless because we are interested in dealing with live people, and live people moves. So knowing where is the camera in the galaxy is useless.
Okay.
What you need to know is where is the camera with respect to the body surfaces, and this is what this is providing. The 3D pose of the camera with respect to the body surface is what you need as a doctor.
Okay. The second question is that I knew something about the nerve technology, and you also use them in the 3D reconstruction. And how do you consider the connection between the nerve technology and the SLAM technology? I know that the NVIDIA do something like the block nerve, and they scan our city and build a whole 3D reconstruction of the city. So how do you consider this technology?
Oh yeah, as I have seen here, the input of the nerve technology is that you need to know where the cameras are.
Yeah.
And this is what this map is providing. So to do nerve, first you need to know where the cameras are, and then you apply those poses to estimate what is the, well, to generate new images, but if you dig in this model, you can compute the 3D surface. So the input is camera poses, and we are able to provide those camera poses.
Oh, I see.
This is the starting point.
Thank you. If there is no other question, let's thank Professor Montiel for his great presentation again.
Thank you.